Okay, so I'm going to give us maybe 1 or 2 more minutes for more people to arrive. It's still Intro to Statistics. It's week number 10. And we're looking at sheet 10. And I'm thinking about doing question 2, question 4, and question 5, depending on time. Those are the questions on hypothesis testing. So about trying to decide whether 2 sets of data have the same mean or some kind of other property with different assumptions. And we'll see how our assumptions change how we calculate those confidence intervals. I'm going to leave question 1 because I think it's fairly self-explanatory. And guides you through quite nicely. And I'm also going to leave question 3 because I think question 3 is some revision on biased and unbiased estimators, which I think we've done a lot of. So we've just got 2 more people waiting to come in, and then we will crack on. Okay, so let's switch over to the visualizer. So also apologies if there's a little bit of background noise today. We've got some people digging up the street outside, and also some people collecting some rubbish as well outside. So it's all a bit noisy out the front, which I wasn't anticipating at all. So if you can hear that, my apologies. Okay, so question 2. So question 2, we were given 2 sets of data. And we were told how many elements of each of the samples there were. So what the mean value and what the sample standard deviation was in each case. Oh, we've got a couple more people I need to let in. And we were also told that we couldn't assume that the data itself was normally that the underlying data was normally distributed. So we needed to use the confidence interval for the difference between 2 non-normal means. And we were asked to calculate, assuming that both the population variance and also, the population variances were different, and then separately that the population variances were the same. So we'll see how those assumptions are influencing what we do. Okay. So just to summarise, the data we were given in the question. Oh, let me get that in focus nicely. That's better. Okay. So the data I was given was I had from data set A, 150 observations with mean of 1386 and a standard deviation of the sample of 114. And then from sample B, I had 200 observations with a mean of 1218 and a standard deviation of 98. And in this question, we were actually given all of those values quite nicely presented. Sometimes you're going to get questions where that information is in a paragraph of text. And the first thing you're going to want to do is to find all of those things that you need and to sort of label them appropriately for what you okay. So the assumption that we had was that that we can't assume normality. So
I just remember saying that. Yeah.
Oh, does somebody have a contribution, or is somebody's mic? Okay. So feel free to, say something in the chat if I'm talking complete nonsense, or take yourself off mute and let me know if I'm talking complete nonsense. Or if you can't see what I'm writing, or anything like that. And also don't forget that Hayden's here. So Hayden's one of our graduate teaching assistants, and she's sat in the background there. You can direct message Hayden if you think I'm saying anything that's not reasonable. You can also just talk to her about the questions that we're not going through as well, or if you're just completely lost and you can't keep up and you want to ask her about anything that's come up previously, also do that as well. I think she'll try her best to help in all of those circumstances, but there might be situations where she's going to say, oh, you're going to need to email Sarah Lees. Okay. So in all cases, we're going to be looking at the confidence interval for the difference between non-normal means. And that's because we've been told we can't assume that the underlying distributions are normal. Okay. So in the first case, we've been told don't assume that the population variances are the same. So we can't say that sigma squared A and sigma squared B are the same. We're not allowed to assume this one. And then we're going to look for a 95% confidence interval. And for a 95% confidence interval, we're taking alpha equal to 0.05. And in this case, because of the assumption that we're not looking at normally distributed underlying data, we can write our confidence interval in terms of Z, 0.975, which has value 1.96. Now, what we need to be remembering is that Z is the value that Z with a suffix like this solves this equation. So it's the value that if we put it into the CDF of the normal distribution gives us whatever value is in the suffix there. So it's an actual number that if we put it into the distribution of the, oh, we've got somebody who's been left outside again. Okay. If we put it into the CDF of the normal distribution, that we get out what was on the suffix. Okay. And with this in mind, if we want a confidence interval for the difference between the two means, so the mean of the underlying data for sample A and the mean of the underlying data for sample B, this has endpoints of the following form. All right, so we're going to want to center our confidence interval on the observed differences between the sample means. So we've got X bar A minus X bar B. And then, as always, we've got a plus or minus. The Z is going to go in there. And the choice of 0.975 is because of the alpha that we've picked. And then we've got something that needs to go in a square root. What we've got here is we're going to have SA squared, so the variance of the observed data in the first set of data divided by the number of elements in the first set of data, and then plus SP squared divided by NP. Okay. So if we could remember that this is the right form that we want to be using, we should have been able to get to an answer here quite well. So we should have been able to just insert the data that we've been given into this formula, which would give us the two endpoints of our confidence interval. And I'm going to leave the intermediate calculation, for you to give a go. But just using this formula is going to give us a confidence interval, which looks like 145.26, comma, on the low end, up to 19074. So we can see from that confidence interval that we were expecting the difference between those two population means to be quite big. We're expecting the difference to be, at least, somewhere in that kind of range. So between 145-ish and 190-ish. So we're expecting those, not to necessarily come from the same distribution. Okay. So the second part, we were asked, so if instead we were allowed to say that we think that the variances are going to be the same, we're going to need to do things a little bit differently. Now, we're going to need to change something in this formula here. And the thing that we're going to need to change is how we're dealing with SA squared and SB squared there. So the first thing we need to do is we need to calculate an estimator for the joint variance. Okay, and then this one, I'm going to denote sigma hat squared. So this one's going to be based on SA and SB. So these two values I was given in the question. And we're going to say, well, what kind of variance do we, if we're assuming that the actual variances are the same, from the observed standard deviations, how can I what's my best guess as to what the joint variance should be? And the form of this one is NA minus 1 times SA squared plus NB minus 1 SB squared. And then I divide everything there by NA plus NB minus 2. Okay. So John says, are we assuming that the population variances are known because of large M and N? So it's approximately the sample standard deviation. So in both cases, we're assuming that the population variances are not known, which is why we're using the S's in the formula for the confidence interval in the first part, because if we knew what the variances were, we would be able to just put in sigma A and sigma B because we'd know what those were. All we're assuming is that they're not the same. And if we're assuming that they're not the same, then we need to use a separate estimate for the variance of the first sample and the second sample. And in this case, when we assume that they are the same, we're not saying that we know what the joint value is, we're just saying that we think that they're the same. That kind of assumption means that we're assuming that there should be one value for, we shouldn't really be saying, oh, we think that SA is the value, is a good estimator for the variance of the first sample, SB is a good estimator for the variance of the second sample, because we think that those values should be the same. So we should be combining the information from both samples to get an estimator for the variance overall, because we're assuming that we think that they're the same. So we can use that extra data from the other sample. Is that kind of helpful, John? Thank you. Fantastic. So, carry on with the questions. That's a good question from John, just to be 100% sure what's going on there. Because these are the things that can change what kind of formula for the confidence interval we need to be using. So the key things that are going to be affecting what the formula is we're going to be using is going to be, do we know what the variances are or not? Do we know whether those variances are equal or not? And also, can we assume that the underlying data is normally distributed or not? And it does feel a little bit like, oh my goodness me, there's like 5 different formulas and they're all like really very, very close to the same. But I think that's where you need to be thinking about, you know, what are the assumptions? Which one do I pick based on those assumptions? And I'm sure you can come up with a pretty good list as to, you know, to help you identify which one you want to be using, you know, from the situation that's described to you. That might be something that Sarah Lees has already provided in the review classes, or it might be something where, you know, you can construct yourself to sort of like help guide you as to what kind of form to use. Okay. So coming back to this second one, where I've written out the formula for an estimator of the joint variance, this sigma hat squared, and we've got these modifying factors in there, this NA minus 1, NB minus 1, and then both of them together minus 2, you know, due to the degrees of freedom issues. So the first thing we want to do is we want to calculate what this estimator for the joint variance is. And then we're going to want to repeat a calculation relatively similar to this. Now, it's not exactly the same formula, but it's kind of similar. So I want to give you a chance at this point to check your answers through. So if you've already done this question, you know, check that you used the right formula here and that you got the right final numbers. If not, substitute the values we've been given into this formula and check that you can get these values out. And then once you've done that, for the second part here, find the number that's relevant for sigma hat squared, the estimator for the joint variance, and then try and decide which form of the confidence interval you should be using, how you need to change this equation, and recalculate the confidence interval. If you get stuck, just let me know in the chat and I can give you a little hint as to what to do. I'm going to give you about 5 minutes to give that a go. And then as we run up to the half-hour point, I'm going to just explain how to proceed, what we can conclude from that, and then we'll start doing another question together as well. Okay, so in this case, the endpoints of the 95% confidence interval so they're still going to have the difference between the observed means in there. So x bar A minus x bar B, and then plus or minus. We're still going to have the Z factor in there because we've still got the assumption about that we can't assume normality of the underlying data. And then this square root term, just got somebody waiting outside, so I'll just let them in. Okay. And then that square root term needs to be changed because we want to replace SA squared and SB squared with our estimator for the joint variances, this one. Okay. And then if I plug all of the values in there, when I calculated this one, I should have got a value of about 11,056. Okay, so if I put this one, NA, NB, etc. in here, I should get the confidence interval of the form 145.4 and 190.26. So this confidence interval is very similar to the previous one. It's just a very tiny little bit smaller. And in both cases, the range there is, considerable. That we've got 95% chance that we think the difference between mu A and mu B is in the range of 145 to 190. So the conclusion that we're looking for in both cases is that the value 0 isn't in the relevant confidence interval. And because the value 0 isn't in the confidence intervals, therefore we can conclude mu A minus mu B doesn't equal 0, is reasonable, is right, plausible, because it's not a 0% chance that they're equal, but we can reasonably kind of assume that they're not going to be equal if 0 isn't in that 95% range. Okay. Right. So moving on to the next question, if you take a look at question 4, we've been given a kind of similar situation. And as I mentioned before, we've got one of these situations where, the information that we need about the sample sizes and the means and the standard deviations is in a paragraph of text rather than laid out for us. I think, let me just double check. Check I've not got that around the wrong way. That was in a paragraph of text in the other one. Now it's in a nice little table. Got myself really confused there. Okay, so we've been given the data about brand A and about brand B. We've got 12 elements in each sample. We've observed a sample mean and a sample standard deviation in each case. And the assumptions that you've been given is assume that that both samples have the same variance. So assume that the underlying variances for brand A and brand B. And we've also been told we can assume that the underlying data is normally distributed. So yeah, assume that the underlying distribution is normal. So that's slightly different than what we've had in question 2. Where we were explicitly told the opposite in question 2, that we couldn't assume that. So again, we're going to need to do something a little bit different with the confidence interval than the previous 2 formulas. So it's not going to be exactly the same as this first one. It's also not going to be exactly the same as this second one. So I'm going to give you guys a chance to give it a go. And maybe spot identify what the difference is. If you've given this a go in advance, just check through what you've got, check that you've not used either of the formulas that we spoke about in question 2. If you haven't given this a go yet, have a think about what you might want to change from question 2, and see what kind of number you get out. If you need a hint, let me know in the chat. If you can tell me what the difference is in the formula for the confidence interval, give that a go in the chat as well. You can do that privately or in front of everybody to give everybody a bit of a hint if you want. And we'll come back in 5 minutes or so with an answer, and then move on to what kind of technique we want to be using for question 5. And after all of that talk of digging up the street, it sounds like the police are coming for Sarah Lee's rather than for me. Okay, so hopefully we were thinking about something very similar to this one. So the first thing we were thinking is we needed a estimator for the joint variance in the same way as before. So we're going to need to do times 11 and 7.5 squared times 11. So it's 11 in each case because we've got 12 elements of the sample. We're also going to have on the bottom 12 plus 12 minus 2 is 22. And the number we need to be using here is 65.97. So that's sort of, you know, the thing that we need to be pinching from question 2 is the fact that we've assumed that the two underlying variances are the same. So we need to first of all come up with a estimator for the joint variance, this sigma hat squared, which we're going to calculate as 65.97. And then we're going to have a formula for the 95th confidence interval. And this is going to be different from the previous one because now we've assumed normality of the underlying distributions. So it's going to have some key features that are the same. It still has the difference here at the beginning. Still has something very similar here with the square root and the factor in the square root. But the main difference is what you're multiplying here by. X bar A minus X bar B. So that remains the same because we're looking for the same thing. We're still interested in the difference between the means of the two sets of data. And I'm going to leave myself a bit of a bigger space now. Okay, so I still need the same factor in the square root there because I'm assuming that I think that the underlying variances, that the underlying population variances are the same. So what is going to be changing is this factor outside the square root. And in this case, it's going to be one of the values from the student t distribution, and we denote it by t 0.975. Now this value here is from the student t distribution. With degrees of freedom 11. And if we look that up in the table, so it's the value such that when we stick it into the CDF of the student t distribution, we get out a value of 0.975. So G 0.975 is in this case going to be, let me just find where I wrote that, 2.074. So that's the main difference there, is that because I've assumed that the underlying data is normally distributed, the factor outside the square root in the endpoints of the confidence interval is now from the student t distribution. And then another difficulty I have there is when I'm looking that up, I need to know what degrees of freedom to look for. And both of my samples are size 12, so I'm going to go for 11. I'm not 100% sure about that. I'm not too sure if that should be 11 or 22. I'm just having a kind of crazy moment. I'm going to just leave them. Okay, so the conclusion that we want to be, so hopefully you got the right formula there for the confidence interval. If you did, when you plug the values in, the 95% confidence interval is going to look like minus 3.98 on the bottom end and 9.78 at the top. So we've got a 95% chance that the difference between the two means is in this range. So the difference between mu A and mu B is in that interval. And 0 is in the middle. That is, it's not directly in the middle, but it is in that interval. So it's possible that mu A equals mu B. Now we can't say for sure that it definitely is, but it's not completely ruled out by the confidence interval. It should be 22. So John says it should be 22, m plus, and Hayden says yes, it's 22. Do you know what? I hadn't made a note of that, and then I just started rambling. So it's 22. Okay. And it does definitely make sense that it's 22 because to use that kind of formula, we don't necessarily need samples of the same size. So we could have a sample of size 10 and a sample of size 14, and we'd still end up with needing to use 22. That makes much more sense, which is great. Okay, so hopefully we all got ourselves through question 4. Okay. Question 5, again, moderately similar, but this time we're looking for a confidence interval for some proportions from the data. So what we've been given is a number of registered voters and a number of people who actually voted. What we're asked to do is to compare the proportions of people who have actually voted. So we don't have enough time to go through it in detail, but I'll start us off just with looking at what we want to be comparing. Now, when you first read a question like this, I think because it's not means, your initial impression might be, oh, don't know where to start. Oh, John's got a good question. Our table only has the values for 20 and 24 degrees of freedom, so how would we find the value for 22 degrees of freedom? Hayden, do you use linear interpolation, or how do you deal with that? Can you answer? Okay. So John, I'm not 100% sure. Hopefully Hayden will type us an answer to us. If not, I'll ask Cyril and make sure that I can be more clear in future tutorials. And I'll ask Cyril just to maybe mention it to you guys, what you should be doing there. Okay. Yeah. So with question 5, we were given 2 values for the number of registered voters. So 288 and 216. We were also given numbers for the number of people who actually vote. And what we were actually asked to compare is the ratios between these. So the estimator that we've got for the proportion of people who vote in the first sample is going to be 141 divided by 288. the same with the second one. We've got p hat 2 being 125 divided by 216. Now, people either vote or they don't vote. So people either vote or they don't vote. So we can be thinking, okay, so this is something to do with the binomial distribution. The number of people in the first state and the second state that vote is going to be binomially distributed with parameters equal to the number of people who are registered and the proportion of them, the actual proportion of them that vote. So the underlying data is distributed binomially with parameters ni, so n1 in the first case, n2 in the second case, and then the proportion of people that we expect to be voting p1 and p2. We don't know what either of the actual proportions are. We've only got the information from our samples as to what those proportions actually potentially look like. And you want to be trying to find a confidence interval for P1 minus P2. So the difference between those two proportions. We want to be, our hypothesis is, are these proportions the same or not? Okay. And I think we're definitely out of time by now, but the approach that you want to try and be taking to that is to use your solution to question 1 yeah, use what was going on in question 1 and maybe check the solutions and either message Sarah Louise or myself if you're struggling with that after the solutions are released later on in the week. Okay, so I'm sorry I've not been able to answer John's question about dealing with the 22 degrees of freedom in the student T distribution. Aidan's pulling a face, so I think she might have just seen that question from John. But I'll see you all next week, and yeah, more exercises next week. If you want to hang around and ask anything, please do. I'll just be here for a couple more minutes if needed. Okay, so I've just found an answer there that says when the corresponding degree of freedom is not in the table that you've been given, you can use the value of the closest degree of freedom that's smaller than the one given. So if in this case we want to be looking up 22, we don't have 22 in the table, we should be looking at the nearest one that's smaller, so we should be looking at the 20 parameter. Okay. And Sarah Lees just says he's contacted John directly about that. Okay, I think I'm going to go and see everybody next week. It might well be the case that Sarah Lees has another tutorial directly afterwards. I'm not 100% sure.
Thank you. Thank you, Jenny.
Okay. Yeah, thank you, Sarah Lees. I feel grateful that I've got to the end of that one. I have found the solution to this issue with the 22 and posted it in the chat. I hope that's the approach that you wanted the students to be taking. Yeah, I'll see you on Thursday.
See you. Take care.
Bye-bye.
Hello, John. Are you still there? No. Okay, you're not there yet. Guys, you okay? Mama, what are you doing?
Hello guys, you okay? How are you doing? Everything okay with you guys? पता है बात No, not many people coming today. So, I don't know what the issue is today. All right, guys. Good morning or good afternoon. Hope you can hear me um, today. Um, so today I'm going to go through the tutorial sheet for week 10, which is sheet number 10. I hope you guys looked at the tutorial sheet. If you haven't, let me show you. This is the tutorial sheet for today. We have a problem once again. This is the tutorial sheet for today, and as you can see, there are 5 questions. I will go through. I will try to do as many as I can, and I will start with question number 5 and work backwards. Okay, as usual. All right. So question number 5 is that here you have 288 voters in California, and out of that 141 actually voted in the presidential election, right? And it also says that there are 216 voters in Colorado, and out of that 125 voted in the presidential election. The question is to construct an approximate 95% confidence interval for the difference in proportions of voting in California and Colorado. Right. Okay. Now let me remind you the confidence interval for 2 samples I talked about last week. I talked about 4 different confidence intervals, and these are the 4. This is the first one. This is for the difference in population means when the variances are known. This is the second one. This is for the difference in population means when the variances are unknown but equal. And this is the third one. This is for the difference in population means when the variances are unknown and not equal. And this is the fourth one. And this is for the difference in population proportions. So for this question, guys, for question number 5, here we are talking about difference in proportions. So the formula that we need to use is this one, right? You guys okay with me? So this is the formula that we need to use for question number 5. So that's what I'm going to do right now. So question 5, if you cannot see, if you cannot hear me or see me, please give a shout, okay? I'm still using somebody else's computer. So this is the formula that I'm going to use in order to answer question number 5. All right, now let's write down what is given to us. So if you go back to question 5, yeah. Now what is given to us is the following: x bar is the proportion for the first sample. So in other words, it's the proportion of people who voted in California, which is 141 divided by 288. And y bar is the proportion of people who voted in Colorado, which is 125 divided by 216. Okay. Okay, and M is the number of voters in California, which is 288, and N is the number of voters in Colorado, which is 216. And we are looking for 100 times, you're looking for 95% confidence intervals, so right, which means that 100 times 1 minus alpha is 95, yeah? And this implies that alpha is 0.05, and this implies that z 1 minus alpha by 2 is z 0.975, yeah? And this is equal to 1.96. Okay, are you guys with me? Okay, so going back to the formula, so what I'm going to do is to sub all this data into this formula in order to get the answer. So let me do that. So x bar is 141 divided by 288 minus y bar, which is 125 divided by 216 plus or minus 1.96. Then the square root of x bar is this. 1 minus x bar is this. And m is 288 plus y bar is this is what you get. All right, so all I have done so far is to sub all the data that we have into this formula, right? Now, if you work this out, guys, so if you work this out using a calculator, you will get this as the 95% confidence interval. Okay. So since the values are negative, I mean this interval is on the negative real line. So it means that the proportion of voters in California is smaller than the proportion of voters in Colorado. Right? That's what, because this, as you can see, this is a on the negative real line, or the whole interval is on the negative real line. Okay, guys, so this is the solution to question 5. Are you okay with this or no? Hello, guys. Any questions you want to? Anything not clear? Please let me know. Hello, guys. Talk to me. Are you guys okay with this solution of question 5? Okay, thank you. Thank you, guys. Thank you very much. All right, the next question I'm going to do. So we're done with question 5. So now we're going to do question 4, right? The computer is still playing. I don't understand why. Are you? Don't understand what the issue is. Sorry, just a minute. Just give me a sec, guys. I got issues with the computer one more time. Just a minute. Give me a sec. Okay. All right. Hopefully it's better now. All right. Question 4. All right. Let's look at question 4. So here you got two brands, brand A and brand B, right? And we are trying to compare the two different brands. And you are told that that the absorption time, the mean absorption time for the two brands have these statistics. So these are the number of data points, and this is the sample mean, and this is the sample standard deviation for brand A, and these are the values for brand B, right? Okay, and the question is to find the 95% confidence interval for the difference in difference in population means for the absorption times between brand A and B. Right, now let's go back to this formula sheet, right? So once again, in this question, in question number 4, we need to use one of these 3 different formulas. Which one do you think is the correct one to use? Is it this one, where variances are known, or this one, where the variances are unknown but equal, or this one, where the variances are unknown and not equal? So which of these 3 formulas should be used and why? I mean, that's a very crucial step of every question on confidence interval. You need to figure out the correct formula. If you don't figure out the correct formula, then you get no credit. I mean, for whatever you do, right? Right, now, if you read the question, it says, one crucial thing it says is that the two brands are normally distributed with a common but unknown value of sigma squared. Do you see this, guys, here, right? What this means is that we need to use the second formula. So this is, excuse me, this is the only formula where we are assuming that the variances are unknown but equal. And that's exactly what this question is saying. It's saying that the two brands are normally distributed, that the absorption times for the two brands are normally distributed with a common but unknown variance, right? So I'm going to use, so this is question 4. I'm going to use the formula, which is the formula number 2, x bar minus y bar plus or minus t m plus n minus 2, 1 minus alpha over 2 sp. This is the formula I talked about last week, right? So let me put this in a box, right? Okay, guys, now x bar is given to us is the mean absorption time for brand A as 21.8. Y bar is given to us as 18.9. M is given to us as 12. N is given to us as 12. Right now, we need to figure out SP. Remember, SP is the pooled sample standard deviation. And the formula for this pooled sample variance is, remember the formula that I gave you last week. This is the formula for the pooled sample variance, right? Okay, now I'm gonna use this formula to compute the, okay, so m minus 1 is 12 minus 1, which is 11. Sx squared is the sample variance for the brand A, which is 8.7 squared plus 11 times 7.5 squared divided by m plus n minus 2 is going to be 22, right? Right now, if you work this out, guys, using a calculator, this is what you will get. Okay, and finally, we are looking for 95% confidence interval, which means that 100 times 1 minus alpha is 95. So your alpha is 0.05, and you need to read this guy here, the value for the t distribute, the percentile of the t, right? So it's gonna be t 22 degree of freedom. 1 minus alpha by 2 is 0.975. Now you should be able to read this from the table. Remember, a couple of weeks ago, I showed you how to read values of the t percentiles using the table. The table is on the course website. You should go to the course website and look at, there's a link called formulas. And if you click on that link, it will take you to this table, right? And if you read the table, you will get this as the value, 2.074. Is that right, guys? So it's just go to the course website, click on the link. There's a link called formulas, and go to the very bottom of the link. You will see a table for reading this, right? All right, so we got everything. So I'm gonna now use this formula, right, and sub in the data, right, that we have. So X bar is 21.8 minus Y bar plus or minus 2.074. SP is the square root of this, right? And then 1 divided by 12 plus 1 divided by 12. Okay, and if you work this out, the 95% confidence interval is from this to this. All right, guys, so this is the answer to question 4, right? So this is the 95% confidence interval for the difference in population means of the absorption times of the two brands A and B, right? So since this interval contains the value 0, but this is negative, this is positive. So since it contains the value 0, you may say that they are not significantly different, right? So the mean absorption times for the two brands are not significantly different from each other because the interval contains the value 0. Okay, so that's the conclusion for question number 4. All right, are you okay with this or not? Hello, guys, talk to me, please. You want to ask me any questions on question 4? You okay? Okay, thank you, guys. All right. All right, the next question. So we're done with question 4. The next question I'm going to do is question 3. Question 3 is this guy here. So you're given these two estimators. This is an estimator for mu. This is an estimator for sigma squared. And you have this random samples x1 to xn and y1 to yn from a population with mean mu and variance sigma squared, right? Okay, and the question is as follows. There are two parts. The first part of the question is to show that the two estimators are unbiased. All right, so let's try to do that first. So this is question 3, part 1. All right, so we want to show that mu, okay, the first thing we want to show is that mu hat is unbiased. Now, mu hat is given by the formula, right? Excuse me. It's given by this formula here, n x bar plus m y bar divided by n plus m. So this is the formula. This is the formula for mu hat, right? And we want to show that this is unbiased. Now remember, to show that something is unbiased, you need to show that the bias of it is equal to 0. All right. So that's what I'm going to do. All right. So this is the difference. Okay. Now taking the expectation inside, this is what you will get. Okay. Now the x bar, we know that x bar is x bar is 1 over n times the sum of xi's, right? And we know that y bar right? Now taking the expectation inside the bracket, you will get okay, this is what you will get. Now these two guys cancel, and so are these two, right? So you get this to be this, right? And then you get this to be this, right? Now mu is a constant with respect to I. So what you have is n times mu, and this is m times mu. Okay. So this is clearly equal to 0. All right. So hence we have shown that mu hat is unbiased for mu. Right, guys? Are you okay with this? So I mean, we did so many questions on bias. You may recall, I think I did more than 20 questions on, I mean, more than 20 examples on bias and MSC. So this is it should be easy for you guys. So it's just taking the bias and showing that is equal to 0. So all right. Okay, so that's the first part. Right. The next, we also need to show that the the sigma hat squared given by this is also an unbiased estimator. So let me write it down first. So this is the estimator. All right, and we need to show that this estimator is unbiased too. All right, so to do that, I'm going to compute the bias, which is the expectation of the estimator minus the parameter that you're trying to estimate. All right, so this is the expectation of okay. All right, guys. Now taking the expectation inside, this is what you will get. You will get in brackets n minus 1 times the expectation of sx squared plus m minus 1 times the expectation of sy squared. Okay. Right. Now you may recall from week 2 or week 3, one of the things I showed you in week 2 or week 3 of this course is that the expected value of the sample variance is equal to the population variance. If you don't remember this, please go back and look at it. And also similarly, the expected value of this is also equal to the population variance, right? Okay, so you have this, right? And this is equal to 0. All right. So once again, we have shown that this estimator is unbiased for the population variance. Okay. Are you guys okay with this so far? Hello. Hello, guys. Are you okay? Okay, thank you. All right, the second part of the question. Okay, so just the first part of question 3. Okay, the second part is so we're done with this, is to obtain an expression for the variance of mu hat and say what happens at both n and m go to infinity. All right, so let's try to do that. So this is part 2 of excuse me. So this is question 3, part 2, right? So we have this estimator mu hat, which is right, which is this, and we want to find the variance. We want to find the variance of this. All right. So it's the variance of this, right? Now, taking the variance inside, this is what you will see. Okay, right? You see, whenever you pull a constant, I'm sure you guys know this, whenever you pull a constant outside of the variance, you need to square it. So that's why you get all these all these squares, right? So this becomes x bar, you guys know, is 1 over n times the sum of xi, right? And y bar is 1 over m times the sum of yi. Okay. Right now, you should pull the constant. Okay, before I do that, let me. If you pull the constant n outside of the variance, you get 1 divided by n squared times the sum of the variance of xi. Yeah. And similarly here, you get, if you pull the constant m outside of the bracket, you get 1 divided by m squared times the sum of the variance of yi. Right? So these two guys cancel out, and similarly these two guys cancel out. All right? So what you have is now variance of xi, the question says is sigma squared. And similarly, the variance of yi is also sigma squared. Right? Okay, so this will be, now this is a constant, so the sum of a constant is n sigma squared, and sum, again, this is m sigma squared, right? So what you have, the final answer is sigma squared divided by n plus m. And this clearly approaches 0 as n goes to infinity or m goes to infinity. All right, so this completes the part 2 of question 3. Are you okay with this, guys? So this one, hello guys, are you okay with question 3? This is the solutions to question number 3. If you're not okay, just let me know. I'm happy to go over happy to go over the material with you again. I mean, I really want you to learn very good in this course. So if this is not okay, please let me know. Okay, right. All right. So the next question I'm gonna do, guys, is, so we're done with question 3. So we're done with question 3. So the next one I'm gonna do is question 2. So here you have two different brands, A and B, and this is about mean lifetime of light bulbs. So you have 150 light bulbs from brand A, and their mean lifetime is this, and the standard deviation is this. And you have 200 light bulbs from brand B, and the mean lifetime is this, and the standard deviation is this. The question is to find a 95% confidence interval. First, assuming that the variances are not equal, and second, assuming that the variances are equal. Right, so let's see, okay, let's look at the first part where the variances are not equal. So this is question 2, part 1. Now, let me go back here, right? We are trying to compare the mean lifetime of bulbs, right? So obviously the formula that we need to use, sorry, just a minute, Harry. The final answer for question 3 is this one, Harry. This is the final answer for question 3, part 2. And as n or m goes to infinity, this goes to 0. All right. Okay, coming back to question 2, guys. So here we are trying to compare the mean lifetimes of 2 different brands, A and B, okay? So obviously the formula that we need to use is either this one or this one or this one. Now for part 1, in part 1, we are assuming that the population variances are not equal, right? Now, which of these you think you should use and why? Can you tell me why? Is it this one or this one or this one? Okay, here we are assuming that the variances are known. Here we are assuming that the variances are unknown but equal. Okay, and here we are assuming that the variances are unknown and not equal. So of these 3 formulas, which one applies to part 1, you think? Hello, man. Just feel free to, is it gonna be 1 or 2 or 3? Talk to me, guys. Just trying to have a chat with you guys. I mean, trying to, yeah. Yeah. Because, all right, let me read the question one more time. If I mean, why are you not answering my calls, guys? The question is this, right? You got 2 different brands, right? And this is the mean lifetime from the first brand, and this is the standard deviation for the second brand, and this is the mean lifetime for the second brand, and this is the standard deviation from the second brand. And the question does not say anything about the population variances being known or not known, right? So as the question reads, right, from the reading of the question, we need to assume that the population variances are not known. Okay, so that means we need to use number 3, right? The formula number 3, because in part 1, we are assuming that the population variances are not equal. So we need to use this part, right, to answer question 2, part 1, right? Is that clear? Okay. So let me show you how to do it then. So the formula that we need to use, guys, is this one: x bar I mean, this is a very important step. I mean, trying to determine which formula to use is a very, very important step. If you get this wrong, then everything you do will be wrong too, right? Okay, so okay, now let me write down. X bar is given to us as 1386, and Y bar is given to us as 1218. Right, and we are also told that Sx is the sample standard deviation, is 114, and Sy is the sample standard deviation for the second brand, is 98. And M is the sample size for the first brand, is 150. For the second brand is 200. Okay, so these are all the data that is given to us, right? Okay, now I'm going to apply a trick here. The thing is, you see, these sample sizes, 150 and 200, are pretty large numbers. They are very large numbers. I mean, in statistics, anything above 25 is considered large. So certainly these two numbers are very large numbers in statistics, right? So what I can do is you can approximate this formula above as follows. right? All right. You see what I have written? Because this is something that I talked about. I don't know if you remember this. Uh, if you look back in the video on the student T distribution, this is a property I mentioned in that video. If you don't remember remember that, please go and have a look at it. Right? That is the student T variable can be approximated by the standard normal variable if the degree of freedom parameter is large, right? So that's what I have used here, guys. So I have approximated this formula by this formula, given the fact that M and N are pretty large numbers, right? Okay. All right. Now, this formula is much easier to compute, right? Okay, so this is going to X bar is 1386 minus Y bar is 1218 plus or minus. We are looking for, I think the question is saying what? The question is ask, okay, 95% confidence interval. So this guy here will be 1.96. Then in square root, you have 114 squared divided by 150 plus 98 squared divided by 200. Right, this is what you have. Now this, if you use your calculator, this simplifies to 145. This is the lower limit, and the upper limit is 190.74. Right, guys? How big is big enough? Bailey, yeah, it's over 25. Anything over 25 is big enough, Bailey, yeah. So, I mean, as I said, in statistics, anything that is greater than 25 is considered large enough, right? So certainly these two numbers are large because they are much bigger than 25, okay? Any other questions, guys? Please. Any other questions? Are you okay, guys? Are you okay with this answer? How I got this answer? So this is the 95% confidence interval for the difference in uh, between the two brands. I mean, in this case, we are comparing the mean lifetimes. So the difference in mean lifetimes of the two brands A and B has this 95% confidence interval. So this is only part one. All right, now part two. Let me now show you how to do part two. So this is question two, part two. Right, in part two, we are assuming, you should go back to the question, guys. We are assuming that the variances are equal, right? So for this, to do part two, we need to use this formula here, right? Okay, because this is the only formula where we are assuming that the variances are equal, right? So the formula that we need to use is X bar minus Y bar plus or minus T M plus N minus 2, 1 minus alpha by 2. SP is the pooled sample standard deviation, and this is the formula. And once again, since this guy is a very large number, remember M is 150, N is 200. So this is a very large number. You can approximate this by the standard normal percentile. It's the same reasoning as in part one, all right? The reasoning being that since the degree of freedom parameter is so large, right? Okay, this can be approximated by this. This is the property I talked about in the video on student T. So if you don't remember, please go back and look at the video. Right now, okay, the only thing we need to work out here is SP, right? SP, to work out SP, I'm going to use the formula for SP squared, which I'm sure you remember is M minus 1 times
m minus 1 times sx squared plus n minus 1 times sy squared divided by m plus n minus 2. Okay, this is the formula I gave you, right? And so if you work this out, guys, this will be m is 150, so this is 149 times 114 squared plus 199 times 98 squared divided by m plus n minus 2 is 150 plus 200 minus 2. Now, if you work this out, this will be 11056.32. So this is the pooled sample variance, right? Okay, now I'm going to use this formula. This is the formula I'm going to use to compute the confidence interval. So x bar, we know from part 1 that x bar is 1386, y bar is 1218, plus or minus 1.96. We know that from part 1, multiplied by SP is the square root of this. So it's going to be the square root of 11056.32. Then 1 divided by m, m is, it's 150, and n is 200. Okay. Now, if you work this out, using a calculator, this is what you will get. So the lower limit is, this is the lower limit of the confidence interval, and this is the upper limit of the confidence interval. Right? Okay, guys. So this completes part 2 of question 2. Are you guys okay? Are you guys okay with this? So the interpretation here is that the mean lifetime between brand A take away brand B, right, has this as the 95% confidence interval, which clearly means that the brand A is better than brand B, because this interval does not contain the value 0. So hence, since this interval is on the positive real line, okay, it clearly implies that the brand A is significantly better than brand B. And the same thing in part 1. In part 1, you see, we got this as the confidence interval. And again, this interval is on the positive real line, which means that brand A is significantly better than brand B in terms of lifetime. So it lasts longer. In other words, the light bulbs produced using brand A are significantly better than those produced using brand B. Okay. Okay, guys. Any other questions, guys? Is it help you? Any other questions on question number 2? Hello, guys. Talk to me, please. Are you okay? Are you okay with question 2? All right. The next question. The only question I haven't done. The only question I haven't done is question 1. Right. Question 1 is pretty straightforward, but if I have time, I only have a couple of minutes left. I will. Okay, this is question 1, part 1. Now here, you have a random sample from a Bernoulli distribution, and you're trying to construct a confidence interval for P. And now you may recall from last week, the confidence interval for a proportion, population proportion. Yeah, that's because, Harry. Okay, I got your question, Harry. That's because the population parameter Harry, the population parameter that we are trying to construct here is the difference between the mean lifetime of brand A and the mean lifetime of brand B, right? So it's like A minus B. So if A minus B is positive, right, that means A is better than B. Do you follow what I'm saying, Harry? Because the parameter that we were looking at, just a minute, it's giving me. The parameter that we are looking at, Harry, is uh, is the population proportion. So the mean lifetime for brand A minus, excuse me, still giving me trouble. I don't know why this computer is still giving me trouble. Sorry, I don't know whether you can hear me or not, but I hope you can hear me now. But I hope you can hear me. Just a minute. The thing is, okay, what I was trying to tell you, Harry, is that what I was trying to say is that the the parameter that we were, the parameter um, that I was trying to construct the confidence interval for is the mean lifetime for parameter A minus take away the mean lifetime for parameter B, sorry, brand B, okay? So it's the mean lifetime for brand A, take away the mean lifetime for brand B. So if that difference is positive, Harry, that means that the mean lifetime for brand A is greater than the mean lifetime for brand B. Hence, brand A is better, right? I hope you get it. I mean, if you did not get it, then please send me an email later. I will try to explain better. But what I was trying to say to you, man, is that since the confidence interval is positive, right? Uh, it means that the mean lifetime for brand A is greater than the mean lifetime for brand B, right? So hence, brand A is better than brand B, right? Okay, significantly. I hope. I mean, if you didn't get my explanation, please get back to me later, Harry. Okay. I think we have run out of time. So question one, I don't have the time to do it, but I will post the full solutions to all the 5 questions on Thursday of this week. So you should go to the course website on Thursday. You will see the typed solutions, the handwritten solutions, and the video solutions for all 5 questions. Okay, guys, so have a great day and have a great morning or afternoon or evening, wherever you are. And any questions, as usual, please feel free to contact me 24/7 by email, Skype, Zoom, or phone. All right. And you know my phone number is 0161 273 2941. All right. All right, guys. So I'll talk to you shortly and have a great time. Um, Good morning, guys. Or good afternoon. Um,
Right. So this is the tutorial for week 10, and this is the tutorial sheet number 10. Um, as you can see, there are 5 questions. I will go through I'll try to go through all of them if I can, if I have the time. So as usual, I will start with the question number 5 and work backwards. All right. So question 5. I don't know if you can see this, but if you cannot see this, please look at the course website. Right. All right. Question 5 says the following: that you have 288 voters in California, and of them 141 voted in the presidential election. And you have 216 voters in Colorado, and of them 125 voted in the presidential election. The question is to find the 95% confidence interval for the difference in proportions of voting in California and Colorado, right? Okay. So to do this question, what you're looking for here is the difference in proportions, right? Now, let me go back to what I talked about last week. You may recall from last week that these are the formulas that I gave you for two sample confidence intervals. So this is the formula that applies when you're looking for difference in population means and the variances are known. And this is the formula that applies when you're looking for difference in population means when the variances are unknown but equal. And this is the formula that applies looking for difference in population means variances are unknown and not equal. And finally, this is the formula that applies when you're looking for differences in population proportion, right? So of these 4 different formulas, the one that applies to question number 5 is clearly this one, right? Because this is the only formula that applies to difference in population proportions, right? So I'm going to show you how to use this formula to answer question 5, okay? All right, so let me put this over here. So this is question 5. So the formula I'm going to use is the following. All right, this is the formula I'm going to use, as I said. Now, let's write down what is given to us. X bar, remember, X bar is the sample proportion for the first population, which in this case is California. So it says California 141 out of 288 voted. So the proportion is 141 divided by 288. And Y bar is the proportion for Colorado. And it says that 125 out of 216 voted. So it's 125 divided by 216. Okay, it's Y bar. Now M is the sample size for California, which is 288. N is 216. Okay, and we're looking for 95% confidence interval, which means that 100 times 1 minus alpha is 95. Okay, so this implies that alpha is 0.05, and this guy here is Z 0.975. Now, if you read this off the normal table, which you have on the course web, if you go to the course web page and click on the link formulas, you will get to the normal table. This will be equal to 1.96. Right?
Okay, this is all right. Now, so we got all these are all the data that we have. So what we have to do now is to sub this data into this formula, right? So X bar okay, X bar is 141. M is 288. Y bar is okay. This is what you have. Right? I just subbed all the data into this formula. And if you simplify this, this is what you will get. The lower limit will be this, and the upper limit will be minus 0.0015. Right? Now, as you can see, this interval is on the negative real line, which means that the proportion in California is smaller than the proportion in Colorado, right? So in other words, the proportion of people voting in presidential election in California is significantly smaller than the proportion of people voting in Colorado, right? Okay, guys. So, are you okay with this solution? Not okay? Please let me know. Yeah. Hello, guys. Talk to me. Are you okay with this or not? Thank you. Right. Okay. Great. How do we analyze the interval found? Yeah, that's what I was saying, Jim. Sorry, I was saying, Vincent, that this is a 95% confidence interval for the difference in population proportion, which means that the difference in the two proportions lie between these two limits with 95% confidence intervals. All right. And since this interval is negative, it's on the negative real line, it means that the proportion for California is significantly smaller than the proportion for Colorado, right? Okay. But to interpret this interval, you can just say that the difference in the two proportion lie between these two limits with 95% confidence. Yeah. Okay. Okay. So that's that's the interpretation, Vincent. Okay. All right. The next question. So I'm done with question 5. The next question I'm going to do is question 4. So here you have two different brands, A and B, and we are trying to compare the mean absorption times for the two different brands. And you're given the data, you're given this data, that is the number of data, the sample mean, and the sample standard deviation for brand A, and the same thing for brand B. And the question is to find a 95% confidence interval for the difference in the mean absorption times, right? And you are also told, the crucial part of this question is here. You're told that absorption times are normally distributed with a common but unknown value for sigma squared. So this is the crucial part that you should read, right? And this part here tells you which confidence interval we should use. So you should go back to this formula. We are looking for the difference in population mean. So it has to be one of these three formulas, either this one, or this one, right? Now, because we are assuming that the variances are unknown and equal, that's what it says here. See, we are saying that the variances are unknown, but they are common, meaning they are equal, right? All right, so the one we need to use formula that we need to use is this one. Okay, this is the formula that we need to use, right? So I'm going to show you how to apply this formula to do question 4. Right? Are you guys okay? So this is question number 4. All right. So the formula that I'm going to use, let me write it down, is x bar minus y bar plus or minus t This is the formula that I'm going to use, okay? Right. Now let me write down the things that are given to us, right? Okay. So x bar is the sample mean for brand A, which is given to us as 21.8. Y bar is the sample mean for brand B, which is given to us as 18.9, right? And yeah, the M is the sample size, which is 12, and it's also 12, right? Now, in order to use this formula, we need to compute SP. Remember, SP is the sample, is the pooled sample standard deviation, right? And is given by the following formula. You may recall this, right? This is, if you look back in the notes for last week, you should try to, I mean, you will be able to remember this. Yeah, this is the formula for the pooled sample standard. Pooled sample variance, right? So given the data that you have, m minus 1 is 11, sx squared is given in is 8.7 squared, okay, and m plus n minus 2 is 20, 20, right? Sorry, not 20, I mean 22, 22, right? Because it's 11 plus 11 minus take away 2 is 22, right? Right now, if you do the math for this, this is what you will get. You will get 65.97 as the answer for SP squared. All right, the next thing that we need is this guy here. This is the percentile of the T distribution. And about 2 weeks ago, I showed you how to read this off the table. The table for T is once again is on the course website. So you should go to the website and look at the link. There's a link called formulas, right? And if you read, you can read this from that link. So you go to that link and there's a table for the T distribution. And if you read it, this is what you will get, 2.074. This is the value that you will get for this guy here, right? Now putting all this data into this formula, okay, this is the answer. Well, the thing that you will get is the following: is 21.8 take away 18.9 plus or minus 2.074. SP is the square root of this guy, which is yeah. Now, if you work this out, the interval will be from minus 3.98 to plus. So this is the lower limit and this is the upper limit, right? Okay. So since this interval contains the value 0, okay, since it contains the value 0, the conclusion is that the two brands, in other words, the mean absorption times for the two brands are not significantly different from each other. That's because this interval contains the value 0, right? Okay. All right, guys, are you okay with this, or are you I mean, if you're not following, it's not in the table. Yeah, it's okay. If this is not in the table, then you look for the closest value. So if 22 is not in the table, then you look for something that is closest to 22, sir, right? So if you go to the table and find something that is closest to 22, you will get something close to this. Or you can use R. You know, in R, to read this command, you use the command Qt as 0.975 with the degree of freedom equal to 22. So if you use this command, sir, if you use this command in R, you will get 2.074. Yeah, I know. I know there are calculations for the t distributions in the internet, but I think it's much easier to use R, because R is free, right? Yeah, R is free, so you can use. It's easier to use R with this command Qt in brackets 0.975 comma df equal to 22. But like if you don't have R, then you can look up something that is closest to 22, like 20 or 24, for example. Okay. All right, guys. Any other questions? Okay. Are you okay with this? Yeah. Okay. All right. The next. So I'm done with question 4. The next one I'm going to look at is question 3. Question 3 is this guy here. You have 2 random samples from a population with mean, mu, and variance sigma squared. And these are the sample means, and these are the sample variances. And you have these 2 estimators. This is the estimator for mu, and this is the estimator for sigma squared. And the question is to show, okay, there are 2 parts. The first part is to show that the 2 estimators are unbiased. We'll get to the next part later. All right, so let's try to do the first part. All right. So this is, all right, this is question 3, part 1, right? So you have this estimator mu hat equal to n x bar plus m y bar divided by n plus m, right? Okay, and we want to show that this estimator is unbiased. Now, remember, I did more than 20 examples, I mean, on bias and MSc. So you should remember how to do this. So to show that this is unbiased, right? We need to show that the bias is equal to 0. So that's what I'm trying to do here. So this is the expectation of n x bar plus m y bar divided by n plus m minus mu. Okay. Now taking the expectation inside, you will get okay, this is what you get, right? Now x bar, you know, is x bar, you can write it as 1 over n times the sum of the xi's from 1 to n. And y bar, you can write it as 1 over m times the sum of the yi's from 1 to m. Okay. All right, now the next thing I'm going to do is I'm going to take the expectation inside the brackets. So you get
Yeah, are you guys with me? Yeah, yes, you can. You can, Mikhail. Yeah, you can directly write the expectation of x bar is mu, but I'm trying to be more detailed in this in my solution. Yes, you're right, Mikhail. Yeah. Right. So, all right. Now this is gonna be the sum. The expectation of xi is given as mu. So this is mu, and the sum. The expectation of yi is also given as mu. Okay. All right. So you have this. Now the sum of mu is n mu. The sum of mu here is m mu, right? All right. So this is clearly equal to 0, right? So we have shown that the bias of the estimator mu hat is 0. So the conclusion is that mu hat is unbiased for mu. All right, guys. Are you okay with this? Any questions? Hello, guys. Are you okay or not? Hmm? Okay, thank you. All right, the next part, so the next thing that we need to do is to show the same thing for this estimator here, right? So you're given this estimator n minus 1 times sx squared, the sample variance for the first sample. All right. So we need to show once again that this estimator is unbiased for sigma squared. So that's what I'm going to do. So this is the expectation minus the parameter, right? So this is the expectation of yeah, right? Now taking the expectation inside the brackets. Okay, right. And now we know that, okay, this is where the stuff that you did before comes in. You should look back in week 2 or week 3. Okay, one of the things, one of the results that I proved in the class long time ago is that the expectation of S squared, the sample variance, is equal to the population variance. If you don't remember now, please go back and look at week 2, the stuff that we did in week 2 or week 3. You will see that I proved in the class that this is equal to this and is equal to this, right? So yeah, so this is clearly equal to 0, right? So hence we have shown one more time that this estimator is unbiased for sigma squared. Yeah. Okay, guys, are you okay with this? So this is, I mean, you should be familiar with this kind of proof right now. Okay. Yeah.
Okay, good. All right. So the next part, so that's only first part of question question 3. The second part of question 3 is this guy here. Is asking you to find the variance of mu hat and see what happens when n goes to infinity and m goes to infinity. So that's what I'm going to do now. So I'm going to find, so this is question number 3, part 2, right? So we want to find the variance of mu hat, right? Which is the variance of mu hat. Remember, is the formula for mu hat is over here. So it's n x bar plus m y bar divided by n plus m. So I'm going to show you how to do this. All right. Now, pulling the constants outside, this is what you will get. You will get, remember, whenever you pull a constant outside of the variance, you need to square it. You need to square the constant. Okay. Okay, guys. Right. The next thing I'm going to do is the following. I'm going to write x bar as 1 over n times the sum of xi. And like this, all right? Okay, and the next thing I'm going to do is I'm going to pull the n outside of the bracket and the m outside of the bracket. So you will get this. Right, and okay, so these two guys cancel out, and so are these, right? Okay, so this becomes 1 divided by n plus m squared, right? Now, variance of xi, the question is equal to sigma squared. The question says this is sigma squared, right? And right. Now the sum of constants, sum of sigma squared is n sigma squared, and sum of this constant is m sigma squared, right? So this simplifies to sigma squared divided by n plus m. Yeah, and this, you should take the limit as n goes to infinity or m goes to infinity, then right, this approaches 0, right? Okay, are you guys okay with this? So this is the solutions to part two of question 3. Yeah, are you okay or no? Please let me know if you're not okay. Please don't be hesitant. Okay, thank you. All right. All right, so we're done with question 3 now. So the next question, I'm going to look at question 2. So question 2, we have 2 different parts. Okay, the question is like this. You have 150 light bulbs from brand A, and the mean lifetime is this, and the standard deviation is 114. And you have 200 light bulbs from brand B, and the mean lifetime is this, and the standard deviation is this. And the question is to find an approximate 95% confidence interval for the difference in mean lifetimes, assuming that this or this. All right, let's look at the first case where the variances are not equal, right? Okay, so let's go back to the formula sheet here. So this is the formula sheet. There are three confidence intervals for the difference in means, right? This is the interval when the variances are known, and this is the interval when the variances are unknown but equal, and this is the interval when the variances are unknown and not equal, right? So which one do you think we should use to do the first part of the question 2? Go guys, talk to me. We have these 3 intervals, right? Each has different assumptions, right? Okay, so we need to use the third one. Yeah, you're right, Mikhail. So the reason for that is, let me explain. Let me explain why. So this is question number 2, part 1, right? The reason that we need to use the third formula is because the question does not say the variances are known, the population variances are known. It gives you the standard deviation, but these are presumably sample standard deviations. The 98 and the 114, they are probably sample standard deviations, right? All right, so the formula that we need to use, and also the question does not say that the population variances are equal. In fact, they are saying that for the first part, the population variances are not equal. So we need to use the third formula, which is this one. I'm going to write it down. All right, this is the formula we're going to use, right? All right, now let's try to figure out what is given to us. All right, X bar. Okay, just a minute. Give me a sec. X bar is given to us. X bar is the sample mean, right? For the brand A, is given to us as 1386, and Y bar is the sample mean for the second brand, which is 1218. And we are also given the M. M is the sample size, which is 150, and N is 200. Right? Okay. So this is the formula that we're going to use. Let me put this in a box. Okay. Right. Now this you can, okay, I'm going to make an argument here now. Remember these 2 values here, 150 and 200. They're large. They're large in statistics. In statistics, anything, if you have a sample size that is greater than 25, then it is considered large, right? So 150 and 200 are pretty large numbers. All right, so you can, the argument that I'm going to make is that you can approximate this formula here by the following. Excuse me. Okay, you can approximate by this. The reason, that's because of the following fact, which I talked about in a previous video. I will, the video that you have to watch is the is the video on the student t distribution. I mean, if you don't remember this, please have a look at the video on the student's t. What it says is that the student t random variable can be approximated by the standard normal random variable when you have large sample sizes, because m and n here are pretty large. 150 and 200, they are well above 25. In statistics, anything above 25 is considered large. So what I have done is to approximate this by this, using one of the results that I mentioned in the video on t distribution. So if you don't remember that result, please have a look. Right? Okay. So this is the what I'm going to use. Right? This is the formula that I'm going to use instead of this one. Right. Now, we are looking for 95% confidence interval, so which means that 100 times 1 minus alpha is 95. So your alpha is 0.05. So your z 1 minus alpha by 2 is gonna be 1.96. Okay, right? So using this formula here, right, you will get x bar, which is 1386. Y bar is 1218 plus or minus 1.96. The sample variance is M. M is and the sample variance for SY is given as 98. Okay, divided by N, which is 200. All right, so now if you work this out using a calculator, you will get the lower limit to be this, right, and the upper limit to be this. So this is the 95% confidence interval for the difference in the mean lifetimes of brand A of light bulbs under the two different brands. So since this confidence interval is on the positive rail line, what this means is that it means that the light bulbs under brand A are significantly better than the light bulbs under brand B. So in other words, the light bulbs under brand A, they last significantly longer than the light bulbs under brand B. Okay, so that's what the interpretation for this confidence interval is, right? Okay, guys. Yeah, the answer will be similar. Yeah, the answer will be similar, my friend. Yeah. Yeah. If you use this formula instead of this, then the answer will be very similar to this. Yes. Yeah. That's because of this fact that these two are approximately equal when M and N are large. Yeah. Yeah. Okay. Any other questions, guys, on question 2, part 1? All right. So the next part, so I'm done with part 1. Now, part 2 is asking you to do the same thing, assuming that the variances are equal. So in this case, if you go back to the formula sheet, the only formula here of these three, the only one that where we are assuming that the variances are equal is this one. So we need to use this formula here to do part 2, right? So let me show you how to do it. Let me show you how to do. So question 2, part 2. So the formula I'm going to use is x bar minus y bar plus or minus t m plus n minus 2 1 minus alpha by 2 sp 1 over m plus 1 over n. Okay, right. Now, once again, I'm going to use the argument that since m and n are very large numbers compared to 25, they are very large numbers, I'm going to approximate this formula by the following. Okay, so you see what I have done. I have replaced this guy here. I have replaced this guy here by this guy here. The reasoning for that is because the degree of freedom parameter m plus n minus 2 is a very large number, right? Because of these two. So hence we can approximate this by this using one of the results I mentioned earlier on the t distribution. So if you look back on the video on the t, you will see that you can do this, right? Okay. Right, now to work this out, we need SP. SP is the pooled sample standard deviation. To compute that, we need to use this formula here. Okay, this is the formula that we need to use. Now, if you use this formula, m minus 1 is 149 because m is 150. Multiplied by this is going to be 114 squared. N minus 1 is 200, take away 1, which is 199, multiplied by this guy here, which is 98 squared, right? And if you divide this by m plus n minus 2, which is 150 plus 200, take away 2, right? Now, if you work this out, this is what you will get. Okay. All right. So now we have everything. So let me put a box here. Right? So X bar we know from part 1 is 1386. Y bar is 1218. Plus or minus, this is the one that we read before is 1.96, because we are looking for 95% confidence interval, multiplied by SP is the square root of this, which so it's going to be 11056.32, right? And then 1 divided by m is what, 150, and 1 divided by n is 200. Okay. Now, if you work this out, guys, the lower limit will be 145.74, and the upper limit will be 190.26. Right? So once again, the confidence interval is on the positive part of the real line, which means that the mean lifetime under brand A is significantly greater than the mean lifetime under brand B. So in other words, the light bulbs produced using brand A, they last significantly longer than the light bulbs produced using brand B. Right? Are you guys okay with this? Any questions you have? Hello guys, talk to me, please. Are you okay? So this completes the solutions to question 2. All right, so we're done with question 2. So the only question I haven't done is question 1, right? Question 1 is pretty, it's not difficult at all, really. But let me show you. I mean, maybe I'll just do the first 1 or 2 parts. So this is question 1, part 1. Here we have a random sample from a binomial with parameter 1 and p, which is basically Bernoulli. Remember, you should know from probability 1 that you took last year that binomial with parameter 1 is the same as Bernoulli, right? And here we are trying to find the confidence interval for p, which is the population proportion. Now, you may recall from the tutorial last week, right? Do I have a question here? Just a minute. Somebody asked me a question. Yeah. Okay. You may remember from the tutorial last week that the confidence interval for the population proportion is this. I mean, right? This is the confidence interval for the population proportion. Now, in part one of question 1, we are looking for the width. The width of the confidence interval is the difference between the upper limit and the lower limit. The upper limit is this is the upper limit, and minus the lower limit is this one. Okay, and you should take the difference between these two. This is what you will get. You will get 2 multiplied by this multiplied by this, right? All right. So this, because these two guys are constants, right? You can see that these two are constants. So this is proportional to all right. This is proportional to this. So this completes this sign. I'm sure you know what this sign means. This means proportional to, right? Okay. So this completes part 1 of question 1, right? Part 2, unfortunately, I think I seem to have run out of time to do part 2. But I hope you guys can do the remaining parts of question 1 by yourself, right? And if you have trouble, just contact me. But anyway, I will post the full solutions, the full solutions to all the 5 questions on Thursday of this week. So you will see the typed solutions, you will see the handwritten solutions, and also the video solutions for all 5 questions. They will be posted online on the course website on Thursday afternoon or Thursday evening, right? Okay, guys, and have a great time wherever you are. I mean, and as usual, if you have questions, please feel free to contact me 24/7 by email. This sign here, sir, it means proportional to. Vincent, you ask, yeah, this sign here means proportional to. Proportional to. That's what it means, all right? Okay. So as usual, so please feel free to contact me 24/7 by email, Skype, Zoom, or phone. My phone is 0161 273 2941. Okay. Okay. Have a great time. And please do not forget to submit your quiz 9, if you haven't done so. The quiz 9 is due on Thursday at 10 a.m. So please try to do that. If you haven't done it already, please try to do that before 10 a.m. on Thursday. Okay. Okay, guys, have a great day. Take care.